Today's topic is deadlocks in operating system. So for any operating system, we have to see that the system process or in a executing without deadlocks. The overview of the deadlocks consists of system models. The overview of the deadlocks consists of system model, deadlock characterization, methods for handling deadlocks, deadlock prevention, deadlock avoidance, deadlock detection, and recovery from deadlock. So, the chapter objectives is to develop a description of deadlocks which prevent sets of concurrent processes from completing their task. To present a number of different methods for preventing or avoiding deadlocks in a computer system. System consists of resources. Resource types are represented by R1, R2 to RM. So resources may be CPU cycles, memory space, and I/O devices, and etc. Each resource type R1 has W1 instances. Each process utilizes a resource as follows. First, we have to request the resource and we have to use the resource and then release the resource. This is the system model for any process to request the resource. Then deadlock characterization. Deadlock can arise if four conditions hold simultaneously. Mutual exclusion. That is only one process at a time can use any resource. Hold and wait. A process holding at least one resource is waiting to acquire additional resources held by other processes. No preemption. A resource can be released only voluntarily by the process holding it. After that, the process has completed its task. Circular wait. There exists a set P0, P1 to Pn of waiting process such that P0 is waiting for a resource that is held by P1. P1 is waiting for a resource that is held by P2. And Pn minus 1 is waiting for a resource that is held by Pn. And Pn is waiting for a resource that is held by P0. That is circularly waiting for each resource. And the last resource is waiting, in turn, will be waiting for the first resource. So this is called circular wait. Deadlocks with mutex locks. So deadlocks can occur via system calls, locking, etc. So this we have already seen in mutex deadlocks in that is process the critical regions. We have seen this mutex locks. Resource allocation graph. A set of vertices V and a set of edges E. So V is partitioned into two types. P is a set of process P1 to Pn in the system, and R is the set of resource types R1 to Rm. Request edge, directed edge P1 to Rj, Pi to Rj, assignment edge, directed edge Rj to Pi. So resource allocation graph, we have some notations which indicates the process, that is circular circle representing the process, square representing the resource types, and the dots within the square represent the instances of the resource. And if PI requests the instance of R, this is called request edge, that is the process requesting the resource, and PI is holding an instance of RJ means that is resource is assigned to the process. This is called assign edge. So we have four representation. One is circle for the process, square for the resource type, and within the square we will be having dots to represent the instances of the resource type. And then request edge, assignment edge. Request edge means that the process requesting the resource, and assign edge is the resource is assigned to the process. So this is the example of the resource allocation graph. So we have, this is R1. This is the resource which is of one instance. R3 which is of resource which have one instance. This is P1 circle. Process and all represented P1, P2, P3 is represented in circles. And each resource here R2 and R4 is having two instances and three instances respectively, and but R4 is now not assigned to any process. resource allocation graph with a deadlock. So if any cycle formation is there in the resource allocation graph, uh, there is two cases. One it may lead to a deadlock, otherwise it may not lead to a deadlock also. For example, here the P1 is requesting for R1, R1 is requesting for P2, P2 is requesting for R3, R3 is assigned to P3, P3 is requesting R2, and already two instances of R2 is assigned independently to P1 and P2. So once if P1 is freeing this resource, then only it can be allocated to the process P3. So which in turn turns to deadlock. Deadlock means it cannot any process cannot complete its execution, mutually waiting for the resources which is holded by the another resource. Graph with a cycle but no deadlock here. Here also the cycle exists in the resource allocation graph, but there is no deadlock here. That is P1 is requesting R1, R1 is requesting P2, assigned to P2, and also two instances of R1, one is assigned to P2 and another is assigned to P3. P3 is requesting up to, which in turn have two instances. One instance is allocated to P1, so now one another instances is assigned to P4. So it can here it can finish its execution and then free the resources, which in turn can be assigned to the P3. So there will be no deadlock. So the basic fact is that if a graph contains no cycles, so it may lead to no deadlock. Smoothly, all the process involved in the graph will be completing its execution. If graph contains a cycle, if only one instance per resource type, then deadlock. If several instances per resource type, there may be possibility of deadlock or there may be the smooth completion of the process. So these are the basic facts we have about the deadlock, the presentation, that is resource types and process in resource allocation graph.